for the Balluff IO-Link webinar. Sharice Rege is going to present from Balluff. And if you have any questions, please put them in the chat, or you can unmute yourself at the end. So thank you for joining us, and I will hand it over to you. Thanks.
Thank you, Sarah. Welcome, everyone. My name is Shishir Rege. I'm a technical sales specialist with Balluff. Today, I'm going to talk about very high-level concepts about Industry 4.0 or IIoT as it stands, and how it relates to down to the machine level or even at the sensor level with the use of IO-Link technology. So before we get started, I want to make sure we cover these three primary topics today. And during the whole presentation, if you have any questions, either you can write it in chat and we can address it, or if you want to speak up. I don't know, Sarah, if they can speak up during the presentation and ask their questions, that would be fine too. But we want to cover about the big picture, what Industry 4.0 IIoT really mean and how they are related. We will talk about the context of a smart factory, what makes up a smart factory and why a factory differs from a smart factory. And at the end, we will cover how we can boost productivity throughout the life cycle of the smart machines using the technology called IO-Link. So let's start with the 30,000-foot view of an industry. So this is a concept from economics called production possibilities frontier. All that concept means is if you are a producer producing more than one type of item or two products, for example, there exists this curve called the production possibilities frontier. So as long as the combination of products you are producing on this curve, you are producing with the maximum efficiency at minimum cost. Again, I'm saying minimum cost, not optimal cost. So that's what is called the production possibilities frontier. To calculate this production possibilities frontier, they take into account the preventative maintenance time, the current technology levels, the current level of the labor force, their education or their skill set, and all that goes into calculating what is the maximum efficiency that a company can produce at. And this is called the production possibilities frontier. Now, when we talk about the production possibilities frontier, a lot of companies do not produce on that production possibilities frontier. And you talk to any company, they will probably say that they could improve their efficiencies more. And the reasons for not producing on that production possibilities frontier is unavailability of labor force or unplanned downtime. These are the two big things that cause people to not produce on that. With the same token, people ask, what would boost this production possibilities frontier to the new level from where it is today? And the only one factor that affects this production possibilities frontier is access to latest technology. Technology helps boost this production possibilities frontier. And just to take an example, we talk about this Industry 4.0, where the first industrial revolution happened when we started using the mechanical loom or steam engines and those kinds of things. We achieved one level of production possibilities frontier. Then in 1800s, we started the second industrial revolution with the assembly line. That boosted the production possibilities frontier even further. Just an example, if you're producing a car manually, that's the latest technology available at the point in time. You can only produce 5, 10, 20 cars per month. When it went to assembly line production, we were able to produce thousands of cars per month. And now with the third industrial revolution, where we are using automated systems like PLCs and robotics, we are boosting that production possibilities frontier to 1 million cars a month. Maybe I'm exaggerating, but you get the point. And now we are standing at that the cusp on the third and the fourth industrial revolution, where we are talking this fourth industrial revolution comes from connected systems, or which we call the cyber physical systems. That is going to boost the productivity even further. So the main topic in the third industrial revolution was to how can we minimize unplanned downtime. When we get into that fourth industrial revolution, we would be thinking about how can we avoid the unplanned downtime and boost the productivity further. And the three mega trends that driving this industrial revolution, the first is the growing middle class. The middle class is growing. The middle class has lots of needs. So for the first time in ever, the middle class would be the highest class on earth. So by 2028, they are basically saying there would be 5.2 billion people in the middle class. That means they want more, they want it now. That's the want it now syndrome that we have. I mean, all of us probably have smart garages, smart houses, Nest things. So we don't need them, but we want them. And this is the pretty good characteristics of the middle class that is driving this next generation of economy. The second part is the world is becoming flat. That means you have a competition from all over the world for the same products or similar products. So you have to be on your toes to produce at a higher rate and be profitable at the same time to exist. The third portion that is affecting this trend very heavily is, I know a lot of people probably don't know what this is. This is a typewriter. And this signifies a very important point in this mega trend is a lot of our machines and systems are outdated. We are still using them because they work. We don't know when they're gonna fail, what kind of downtime they're gonna cause, but it's still working, so why fix it? That's the other thing that's driving this. Just to take a quick look at, this is a study done by ARC. They estimated about $65 billion of automation systems that are currently in use are reaching their end of life. And this number has been highest since 1938. Yes, we are producing machines that last forever, but that means we are not adopting to the latest and greatest technology that quickly. There is also 4 in 10 manufacturers have little to no visibility in the real-time status of their manufacturing operations. That's pretty drastic number there. And a lot of times we become aware of a problem only after it occurs. For example, if you're running a stamping plant and you don't find the right mold in the right place, or it is not calibrated, then you are causing a downtime. I mean, you only figure that out when you need that mold. And that's one of the big problems that we are not aware of what the problems are coming our way. And the other thing that is been changing drastically recently is less than 5% of the revenue that is generated is spent back into investments for capital equipment. Which is again changing drastically. So this kind of shows that modernization is overdue. So what exactly is that 4.0 in the cyber physical system and how it is going to deliver this higher efficiency? So when we talk about Industry 4.0, it can be componentized into 5 different modules. The first being interoperability. Okay, so diverse machines and systems can talk to each other to optimize the performance of the production line. Okay, we've been doing that. The field bus networks that are out there, Ethernet IP, Profinet, that is helping us have that interoperability amongst a lot of different machines. The second topic is data-driven decision making, where we are collecting a lot of data to understand how our operations are progressing. For years, if you have seen a lot of industrial engineers who are focused on collecting all this data about process and improvements using Six Sigma and all those kinds of Kanban processes, those kinds of things. Those were all data-driven decision-making. Now we are taking that data-driven decision-making to another level, understanding our sensors, the health of the machines, the production line, how we can collect that data and make sure we understand, we error-proof our systems, we do track and trace. The third topic comes as a modularity or decentralization. So designing systems in different areas of the world and bringing it together without having to first test the whole system on the machine builder's plant floor and then deliver it to the customer. We are focusing now on designing this machine separately and bringing it together at the field, and which requires a lot of standardization, a lot of predefined interfaces in order to build those things. The fourth component is the virtualizations. I'm sure you guys have all been to some trade shows where they make you wear the VR glasses and look at the whole system. There's lots of technology that's coming along that is allowing this virtualization to help ease remote diagnostics, to point out troubleshoot areas of the system or machine that are hard to reach or hard to get to in a timely fashion. Again, this is improving that unplanned downtime issue. The last portion that is coming up is the service orientation. I mean, in our personal lives, we are using cloud storage. Almost everybody is using cloud storage and data gathering, accessibility for devices virtually, which is probably same is going to happen in the industry, where there is going to be companies that are going to show up that will offer cloud storage or AI solutions to understand, to read your data, create patterns, and help understand how to improve your processes. This is going to be a critical portion of that Industry 4.0. And this is what actually Industry 4.0 stands for, is primarily these 5 components. When we talk about IIoT on the other side, which stands for Industrial Internet of Things, we are basically talking about collecting information from diverse places. So if you look at our traditional automation pyramid, it always stood up as there is a distinct differences between the field level, control level, process level, and all the way up to enterprise level. And the enterprise resource planning could not get down to that field level or the control level without proper authorizations, without proper interfaces. That was restricting the data flow from one end to the other end. In order for us to, I apologize guys, with lawn mowing outside. In order to connect all these systems together, we have to have that seamless communication throughout the entire organization. And that might look like this, where you have data collection going from the sensor level all the way to the ERP level or the plant level, and making decisions at that level. I don't know if I have, yes, this is a great example. So if you are a runner, you are probably familiar with the Nike's Air Max 90, which can be configured to the nth degree to prepare your shoe. There is about 1 quintillion, 500 and quadrillion, 500 some quadrillion combinations that you could have. Now, when you order that customized shoe, Nike is not going to stop your full run of production, but at the same time, it's going to deliver that configured shoe along with the thousands of same looking shoes that it's producing. These combinations are hard to maintain in any PLC or any ERP system at once. So this is where we are connecting the ERP system to the plant level, saying, sending that one order of a unique shoe that's going to be produced along with hundreds of other shoes. And this is not only for the Nike or consumers, I mean, it's of course consumer side, but not only for the smaller pieces, but even Mercedes offers around 200,000 variations of their S-Class Mercedes, where you can change the seat colors, the seats, the transmission, and all the different things that they can offer. Again, all those combinations are hard to pre-configured or pre-decide and plugged into any type of PLC that, okay, I want this particular combination, let's produce that. This is what is driving the need for having those cyber physical systems which talk to each other through different arenas. So Internet of Things just means that it's a network of physical objects which can collect and transmit data or exchange data through the backbone of Ethernet technology. And industrial Internet of Things kind of condenses it down to the physical objects and things that are exchanging data, collecting and exchanging data at the industrial space. And this is what is called industrial IoT. So when you take industrial IoT and merge it with Industry 4.0, it's basically IIoT stands as a backbone for Industry 4.0 objectives, that is achieving interoperability or modularity, data-driven decision-making for exchanging data across the automation pyramid. Hopefully clears up this 30,000-foot overview of Industry 4.0. Now, let's get down to a factory level or a 10,000-foot level. When we talk about a factory, there is a new concept called the smart factory. How the smart factory differs from the factory. Any factory exists to make profits for its stakeholders or create value for its stakeholders. It's creating products that the customers need. It's providing earnings for their workers, and it is creating profits for their stockholders. If any of these three things don't happen, the factory ceases to exist. Now, with the world becoming flat, there is that fourth dimension that gets added to the factory, and that is competition. If I can't produce in time, my competitor is going to take away that business from me. If I can't deliver it in time, or I can't make profitable decisions in time, my competitor is take over. And that's where that smart factory comes up. And the smart factory relies on two basic things. One is a continuous improvement, and the other one is efficient lean operations. Those are the two foundational things that are needed for a smart factory. When we talk about continuous improvement, we are talking about something called predictive analytics, track and trace, error proofing. So we are looking at the current operations and improving that for the future ones. When we talk about efficient lean operations, that is now. That is, what are we doing now, or what can we do? We can do predictive maintenance or ease of troubleshooting, remote monitoring. All those kinds of things help improve my production plant today. Continuous improvement helps my production efficiencies for tomorrow. So those are the two main basic pyramids for that smart factory. Now, in order to achieve any of these objectives, to do predictive analytics or predictive maintenance or any of those things, what I need is data. And that data comes from multiple sources, but it is about the health of the system, the production data, the maintenance data, and the key point is that data has to be relevant, reliable, and contextual. If I just tell you my sensor is reading 50 degrees Celsius, I don't know if it's the right temperature, high temperature, low temperature, until I put a context to it that, hey, for my process, my temperature range is up to 45 degrees Celsius, and I'm reading 50 degrees Celsius. Now that's high. So, and it has to be relevant in terms of decision making. What do we need to do when the temperature reaches that 50 degrees? Or should we wait and if we find out tomorrow if the temperature was 50 degrees, how the impact is going to be on your product? So based on that data, we can decide where to produce, what to produce, when to produce. We can also deploy resources accordingly, and we can decide what systems or machines we need that needs this maintenance. So overall, we can focus on improving efficiency of the entire factory based on the data. Now the question comes, where is this data coming from in the smart factory context? One place that data is coming from is the machine controller. And the machine controller can only give data what it can access or it can synthesize, which is a production-related data, efficiency data, quality-related data, or general machine health, that, hey, I produced 100 pieces in 20 seconds or whatever, 50 seconds, and my OEE is 96%, which is great. We need that data. But what's missing is how, just before that design is released. Once the design is released, we get into that build phase where we apply a lot of time and resources to build up this controls cabinet, electrical wiring. We route the cables from all the way from sensor back to the controls cabinet, cut it, strip it, ferrule it, crimp it, label it, land it. It's 6 or 7 minutes per landing. And it leads to a lot of human error potential. When the controls engineer come onto this machine for program and commissioning phase, they are spending their initial time debugging problems in the first 2 phases so that the machine is at least ready to be programmed. What happens throughout all this process, we wasted a lot of time. Our customers aren't paying us for debugging those issues, right, in the build phase or design phase. So how can we cut that time down? I mean, if we just take a look at a simple calculation of, say, 50 sensor, integrating 50 sensors, that is 150 wires. That's about 18 hours of time if it takes about 7 minutes per landing. It could be less, could be more. If you take a burden rate, it amounts to $1,500. Then if we assume there is a 15% errors, and that's about $300 to fix that error. So total cost of installing that 50 sensors could lead to about 20 hours of labor time and $1,800 that your customers aren't paying for building that panel or building the machine. If we were to look at this I/O architecture, we can see how we can simplify this design. So this is that generation 1 where you are routing cables all the way back from the sensors to the control panel. Wiring them up takes up a lot of time, but there is no diagnostics information available. You can't tell if there is going to be a short circuit or if there is a short circuit on something. Then in generation 2, we added some passive junction boxes, which shortened the cable length from the sensor to the junction box, but it did not eliminate any of the parallel wiring, because now we are bringing up the bulk cable back to that controls cabinet to wire it up. Then we became a little smarter as an industry. We added this network interfaces with this nice looking network blocks with the short cable runs, single cable for network going back, single cable for power going back to the controls cabinet. We eliminated all these cards from the controls cabinet, and we got status and diagnostics information on board. So we achieved all these objectives of lean manufacturing here with the double-ended card sets. The time and errors reduced drastically, got the status and diagnostics. So when I fire up or power up that system, I can see and fix all these errors. The problem with this was, if it was a digital input module, I can collect up to 16 sensors on one network node. If I need that 17th sensor, I have to put another one of the network I/O block. If I need an analog input, I need to put another one of this network I/O block. So we added up all these cards from inside the controls cabinet, put it out on the machine, and that becomes very expensive quickly. Now we are in that 4th generation where we can collect a variety of different sensors, and this is what we call the I/O link. The network block looks just like the network block from generation 3, but now I can collect discrete I/O if I want, if I can connect visualization devices, analog I/O, pneumatic manifolds, smart sensors, smart devices, everything can be integrated into a single network node. The only reason I would need another off-network node is because my system demands it. So there is enough I/O that demands one more I/O link master. This is what the I/O link master stands for, and or the devices needed. Okay, so that's the advantage that Generation 4 or the I/O link offers in simplifying that entire controls architecture. That I don't need a different type of cable for integrating pneumatic manifolds, or it's all standardized cables, whether it's a smart sensor, dumb sensor, it doesn't matter. It is using that same sensor cable that the previous 3 generations have used. And in order to do that, the biggest benefit that I/O link can offer is standardization of interfaces for entire factory. Uses the same standard cable for multiple types of devices. This is a case study from Ingersoll CM system. This is a little bit older, but they moved from a network-based architecture, so generation 3, to the I/O link architecture, where there is one I/O link master, which is on the network, and then lots of I/O hubs. And it resulted for 60% of cost savings for them. So now they improve their efficiency. They don't have to wire up and program each of the network drop with IP addresses and all these things. They improve their efficiency, they improve their cost. So both the things happen to help them achieve that efficiency, the next level of efficiency or production possibilities frontier that we talk about. Another example from another customer of ours, 4E Automation in Detroit, they build long conveyor lines, and they are utilizing those I/O link masters and I/O link devices, I/O link RFID devices for connecting to entire conveyor line. And they estimated their engineering time savings of about 50% and their labor savings of about 30%. So these are the couple of case studies that showed that there is a possibility to improve your time on the machine as well as reducing your cost of the machine. So what is this I/O link? So I/O link is a point-to-point or peer-to-peer communication. That means from one master port to one device, that's what it can communicate. And it can utilize 3 or 4 wire unshielded sensor cable, the same cable that we have been using for ages. The devices can be about 20 meters away from the I/O link master ports. And then there is that device level communication is completely transparent from the field level communication. It is definitely not a network. That means you can't daisy chain devices just like you can daisy chain the network drops. And it is completely vendor neutral technology. Defined by IEC 61131-9. So it's a standard communication. It's nothing proprietary to Balluff or to any of these vendors. It is a completely vendor neutral technology. So you can have anybody's masters with anybody's devices and they should be able to connect as long as they are I/O link. So what makes I/O link smart is the 3 levels of communication it offers on that single cable. The same sensor cable can be used for process data. So process data is the cyclical communication between the sensor and the master. So if it's a distance sensor, it's continuously providing distance value. If it's a pressure sensor, producing pressure values. The second is the parameter data, which is a acyclic communication, where basically the controller can configure the device for certain things. For example, if it's a pressure sensor and I want to read pressure in bars or PSI, I can set that as a configuration. If I want to set some set points on the sensor that, hey, if the pressure reaches a certain point, give me alert or give me signal, that can be done as well with the parameter data. So it's a messaging instruction. And then the third is event data. So I can also configure some ambient values for that sensor. Say, hey, if you notice higher vibrations than usual, send me an alert. Or if there is ambient temperature goes above a certain limit, send me an alert. If there is a short circuit detected, send me an alert. So that is all that event data or diagnostic coming from the sensor. So the device initiates this communication to inform about the error. So the other advantage you have here is with that process data is communicating actual engineering units versus 4 to 20 milliamp signal that needs to be scaled. And we can take a quick look at analog devices. So typically when we have these analog devices, you have some piezoelectrics, some amplifiers, and this is when the signal is purely in analog form. Nowadays, all these sensors have microprocessors. These microprocessors cannot understand analog. That means that signal has to be converted to digital so the microprocessors can synthesize it. And then comes, how do we transfer that? Well, we graduated with our sensor technologies. We added a lot of microprocessors and other information, but we decided to convert that signal back to analog, ship it over expensive shielded cable back to an analog card that converts that signal back to digital so the PLC can process it. By the way, the work is not done there. Once you receive that signal, it's going to be 4 to 20 milliamps or 0 to 10 volts. We have to put meaning to what that 4 milliamp means, what the 20 milliamp means, and that's called scaling. So the programmers have to scale the data inside of their controller, and the moment you change the sensor, you have to go back and adjust that scaling. So it's not just plug and play, and replace it, and be done. If anybody has a question? Okay. So what if, since that data is already in digital format, because there is a microprocessor involved, why not get that sensor data directly from the sensor and connect it to an IO-Link master? Now I'm using a standard unshielded cable, so it's no more expensive analog cable. It's a 24 volt signal, so it's a higher noise immunity than your analog 4 to 20 milliamp or 0 to 10 volt signal. You don't need any analog modules on the other end to connect, and it is a completely field bus independent architecture. Plus, now that it's no longer a signal communication, it's a data communication, I get to use the benefit of parameter configuration as well as diagnostics. Okay, so I can talk to that sensor to set up some parameters, set up some values that helps me a lot along the way. When that sensor is throwing back the engineering units, of course, it eliminates your scaling. You don't need to convert that 4 to 20 milliamps because you're not getting 4 to 20 milliamps. If it's a distance sensor, it's going to give you microns or millimeters or meters, whatever that set unit is, or inches. It makes the device plug and play, and it saves a lot on the development time and debugging time because, for example, if I have an analog sensor connected and it's always giving me 0 milliamps, I don't know if the sensor is there or not. I'm assuming that the sensor is working. Same goes with the inductive prox switch. We are assuming all the time that it's working. If the wire gets slashed off or cut off, you have no idea whether that sensor is there or not. IO-Link gives you a signal back right away when it detects that, hey, there is supposed to be a device, but there is no device connected. So that's another advantage that the IO-Link offers is your critical processes can be protected well with that smartness in the sensors. Parameterization offers other benefits like set points, selection of engineering units, and signals setting. The other advantage IO-Link offers is called a parameter server functionality, where once you parameterize the server, once you configure that server, you can store that configuration parameters on that port of the master. So when you need to change out that sensor, you just plug in the same type of sensor and it will automatically get reparameterized. Versus in the manual configuration, you have to go in, you have to have some kind of a cheat sheet to set, okay, this is what I need to set these toggle switches at in order to get that. All that work is gone. You are connecting the sensor and it is automatically getting reconfigured. A lot of people ask me question. So it's good, Shishir, that if the sensor needs to be replaced, it can be replaced easily. What happens if the master goes down? Well, if the master goes down, all these IO-Link sensors retain their parameters, the last set parameters as well. So you just replace the master and connect back to the same ports, and they will all be plug and play. They can read the data, store the data again, and it offers that redundancy in the system, so you don't have to back up all this data all the time in the PLC. This is another use case from a customer where they're building a hydroforming machine, so it's a huge analog system. As you can see in the small picture here, this is how that system used to look, the huge control panel with all the wiring going around the thing. Every time they had a problem with the analog sensor, and it's a heavy analog user, every time they had a problem with analog, that control engineer had to come back to work to fix the problems because the maintenance guys could never fix it properly. And it started affecting the quality of the things. Once they moved to IO-Link, now that controls engineer can sleep well at night because all these maintenance guys have to do is to find the right sensor, plug it in, and off they go. So that's helping them a lot with the consistent product quality, efficiency improvement. They don't have to stop the line until that controls engineer shows up. Everything moves smoothly. So that's the advantage of having IO-Link on board. HPUs is another area where IO-Link actually makes sense. And this is actually bringing us to that IIoT world closer. A lot of times these hydraulic power units are installed in wells or basements or some areas which are hard to get to during operations. And manually, somebody has to go to all these HPUs to check the oil levels, check everything is well with them. Frequent monitoring is required. Well, in order to monitor those variables, a lot of times you have to stop the machines so that somebody can go into the basement or the wells and check all these levels. With IO-Link on board, you can plug in these condition monitoring sensors or pressure, fill level, temperature sensors onto the HPUs and collect the data automatically to the dashboard. You don't need a PLC to connect to these devices because IO-Link, the moment you have the power to that master, it is communicating data with the sensor, whether that sensor data is being used by the controller or not. So even if you have a machine controller, you can plug it through a switch and you can also collect that data outside. So this is giving you that condition monitoring dashboarding. So the machine controller can remain focused on machine specific operations, the processing of the data versus collection of condition monitoring parameters or data could be done separately. So we are not bogging down the machine controller to do the condition monitoring or predictive maintenance job. IO-Link is built in to do that functionality. Balluff IO-Link masters are specifically focused on this technology. It offers something called a JSON server. So it's continuously publishing this data to whoever wants to listen to. So basically, when you have the IO-Link master or IO-Link devices, you could use them with the machine controller, or you could create a parallel path just for condition monitoring purposes. So this gives you ability for collection of data for predictive analytics for the future, asset tracking, data logging, all those kinds of things can be done with the use of IO-Link and the smart devices. Here's an example I want to share with you. This is an open source Node-RED application software. Basically, it's collecting data from the IO-Link master directly to this dashboarding tool. So the IO-Link master does not need a PLC or anything. So for example, if this is connected to an hydraulic power unit, there is one master, pressure sensor, flow sensors, temperature sensors, whatever you may have. Data is collected directly from that master to the dashboarding tool. without need of a PLC. So that now you are enhancing the system to give these additional capabilities that were not possible when you had a digital or just a signal communication. With the data communication, now it's possible to get to this level of enhancements with the systems. So having said that, I think I took a lot of your time. Hopefully this was helpful. In order for us to get to that industry 4.0 with our systems, you guys need a smart factories with the smart machines that entails adopting to the technologies of the smarter devices. And IO-Link offers that vendor neutral, field bus neutral interface, which is most cost effective because there's no need for different cabling, different type of things. It simplifies your bill of materials, offers standardization of interfaces. Hopefully it simplifies the integration for you as well, and offers that seamless communication from sensor to the cloud level. If there are any questions, I'm here for a few minutes. Thank you, everyone.
And thank you so much for your presentation. If anyone has any questions, please, you're welcome to unmute yourself or put them in the chat. This will also be emailed out to you, as well as his contact information in case you have any questions that you think of later on. So thank you again for joining us. And we'll wait just a minute or two and see if we have any questions pop up.
All right. Thank you, everyone.
I don't see the questions, so thank you. We'll close the meeting.
Thank you.
Thanks.